When we speak about lithium-ion technology, there are, in our world, three main types. There is NMC-like, nickel, manganese, cobalt, and there is LFP, lithium iron phosphate, with kind of a renaissance in the last years. And then there are also exotic animals in the zoo, like LTO, titanate. Let's look into a battery cell. Let's take a deep look. What happens? So in a battery cell, you have a plus pole, you have a minus pole. You know that from your remote control of the TV. They are connected to whatever is there, a lamp or so. And inside there is a separator, because otherwise you would have an explosion, and a liquid. This liquid is called. If you don't operate your battery, but just let it stand around, let it chill, or as we say, idle. It's not used, it's just standing around. Also, this influence can be heavy. If you let it idle fully charged, 100%, in this case, it will be dead after 800 days.
Hello, everyone. Welcome. Good morning, good afternoon, good evening from wherever you are joining us today. Welcome to today's webinar. Today's topic, the title, Real-Life Examples for Anomaly Detection with Battery Diagnostics. We have 273 people subscribing today for the webinar. Lots of people joining. We see developers of large-scale PV and battery energy storage projects. We see insurers, financiers, EPCs. Warm welcome, everyone. It's my pleasure to be hosting this session for you today. Special welcome to Claudius Jalef, the CEO of Volitica. Volitica is a key player in battery diagnostics. Good morning, Claudius. Glad to have you here. Let me give you a bit of background on Claudius. He formerly worked at Fraunhofer Institute as the energy storage diagnosis and telematics lead. And he's also a frequent lecturer on various battery topics, including battery degradation. And I think one of the ways that we know you is through the Battery MBA program that some of our team members have participated in. Also presenting today is our own Arthur Clare. Arthur is our head of technology at Sinovoltaics. He's based out of Switzerland. He's an energy storage expert himself. Previously worked also here in Hong Kong, and he's on over a dozen of utility scale battery energy storage projects around the world. Also, special thanks to the team that made this webinar happen. Christine Lustig from Volitica, thank you very much, and also from our side, Sylvia, for all the work that goes into organizing such a webinar. My name is Driekes de Rooij. I'm the managing director at Sinovoltaics, based out of Hong Kong. I've been living here in Asia since 2009, and our company Sinovoltaics is best known for performing factory audits, inspections on PV and battery energy storage components here at the factories in Asia. Today's session it's going to be approximately an hour or so, 30 to 45 minute presentation, and then there's plenty of time for questions. If you have a question, please type it here in the chat box on your screen. We'll see those coming in, and we'll try to answer as many as we can. Some of them perhaps during the presentations, if it's relevant. Others we can answer after the session. So please feel free. We're going to make it an interactive session. Just want to check, can everyone hear me correctly? There's one person that cannot hear me. I see it coming in the chat box. I just want to make sure that everyone can hear me. So it seems that the sound is working fine. So if your connection, if If you don't hear me, then try to log in again and it will probably work. So first presentation today is by Arthur Clare, who leads our energy storage team here at Sinovoltaics. Arthur, you will be talking about factory accepting testing, FAT. So let me give the word to Arthur and he will get started. Please, Arthur, go ahead.
All right, thanks a lot, Vickers, and good morning to everyone joining this webinar. I hope you will like it, and we'll discuss today about the frequent BSS issues found during the FAT. So just to be sure everyone is on the same page, when we talk about FAT here, we are not going to talk about how you will lose weight before the summer break. But you are going to talk about the factory acceptance testing for battery energy storage system. So those are about 20-foot, 40-foot containers full of batteries. And when we talk about FAT, it's usually a list of a mix of tests, including visual inspection, as well as a final test to be sure that the performance are good enough. And this step is really important in the life of a BESS, because it marks the transfer between the supplier, who is usually based in Asia, and who is supplying you with the BSS, to you, to the final client, who will then own this BSS for the rest of its life, ideally 10 to 20 years. So we're going to see first why FAT is important, and after, as the title suggests, what are the most frequent BSS issues we found during FAT. But let's start with why. So why is FAT important? First of all, is to find the critical defects that may generate really bad events later in the life of your BSS. So the ones that comes to mind are battery fires that will last for several days. And unfortunately today, as soon as you have a fire, including lithium-ion batteries, your name will be all over the news. So this is the first point why you want to do a FAT, is to ensure that we'll check those critical points. Second is to ensure your return on investment. And here, this is a really interesting point. So you want to check the performance of your BSS is as expected, is according to your BSS specifications. So here for this Valley Center project in the US, it's a bit a funny story, because so the return on investment couldn't be met because one or more containers got decommissioned because of a faulty component. So in this case, it was a faulty sprinkler system. And actually, I said it's a funny story because after those containers were turned off, some battery modules got stolen. So it's really a bad case in terms of return on investment. Last but not least, why you should be really careful about FAT and that you should really focus on that is that today there is no standard for FAT. If you have some experience into BSS, you may have heard about standard like UL 9540, UL 9540A, but those are only specifically done for the design phase of a BSS. There won't be any tests for the manufacturing of your BSS. Meaning that for the FAT right now, it's a bit like I would say like the Far West. Everyone is making its own test. It's a case-by-case basis, really, because so today each supplier has its own test list. And what we have seen through the different suppliers that we have done FAT at is that even the same supplier for two different clients, we won't conduct the same FAT. It will depend on the name of the final client, to be fair, and also of the times that we have for the FAT. Because one critical challenge for the FAT is that in most of the cases, the supplier want to ship as soon as possible because there just has been some delays or because the client just wants to. And in the end, it will squeeze the time for the FAT, which is usually a really bad sign. So what do we do during a FAT? So as I mentioned earlier, it's a combination of several tests. First of all, you will have some visual checks of the BSS. Also after we'll check, so because a BSS component is composed of several components, So we'll check that each component separately is working well, is working fine. So what I mean by that is that you want to check first that the battery module is working well, that the PCS maybe is working well also for the cooling system. And in the end, that's the first step, that you will check everything is working well together through some simple charge and also discharge cycle. And last but not least, you will push the system to the limit through the performance test, and we will also conduct some safety tests as well. And so from that list of items that are being performed during the FAT, we're going to see now which are the most frequent issues that we find. So first one, it's not the most important in terms of the performance of the system, but just like for this T-shirt, when you are buying something like a battery energy storage system, which is worth a lot of money, you want it to look nice. You don't want any design issue. So just like this T-shirt, from what we have seen, unfortunately, we couldn't put pictures here of actual BESS. So that's why I've put this picture of a really nice T-shirt that I really like. To be fair, it's really funny. Is that what issue that we find here is that the name of your company got spelled wrong, or even worse, once I have seen that it was the wrong company name put on the BESS. So just keep in mind, just having this picture of you receiving this BESS in front of your whole company crowd and having the wrong company name spelled on it. So it's really, so again, it's not important for the performance, but you want it to look nice. And also on the right here, you have some smaller issues according to the visual inspections, whatever it is related to the painting or for the damages that we found regarding of bad painting. Second issue. Yeah.
Arthur, if I can interrupt, there's a question from Eric. I think it's a relevant question. Let me pull it up here. He's asking, does FAT in your context mean final acceptance test or factory acceptance test?
It means factory acceptance test. So this is the last test done at the factory.
Right. Okay. Thanks, Arthur.
Welcome. So yeah, second issue, which is major, to be fair, in that the fire safety system is not working. And this is insane to me, but in 1/3 of the cases, we found that the fire safety system is not working, which is a super critical component, as you can imagine, to detect that the battery fire would just take place or not, and just to take preventive actions to shut it down. So again, 1/3 of our inspections, we found that the fire safety system is not working, and this is absolutely critical. So please today call your supplier and maybe check on site for your BESS to confirm that this is working correctly. Third frequent BESS issue is about the software side. That sometimes when we visit factories for the FAT, we found that people are not working on the FAT, but rather on solving some bugs because of some bad software issue. So those software issues could be on two sides. First one is like the whole system according to the BESS with the EMS, with the energy management system. So meaning that how the BESS will work with the PV module, with the genset, with the grid as well, with the load. And you want to be sure that those tests are done before the FAT. On the same side, you want to be sure that the software communicating with both the PCS, so the AC to DC conversion side, with the BMS of the batteries is working well. So here was unfortunately some issues that we find when we arrive. And so instead of working on the FAT, the engineers are working on the software, which they should have done before. And last but not least, of course, we do some performance tests. So we find that in some cases that the performance are not met. So here it's a case-by-case basis. So I don't have typical points to check, but what you want to be sure is that your performances are met. And so, as a conclusion for this small webinar here, some key topics that you can use for your own practices. That so for the FAT, I think a first key point is to align on the BESS test to be performed, and ideally you would put it in your supplier contract. You will not talk about this a few days before the FAT will just take place, because that's the best way to have surprises from the supplier. And to have the FAT not be done in the ideal conditions. Second, it's really critical, I think, is to always have someone on site to confirm the FAT results. So just have someone from your team or from third party, like for example, our company Sinovoltaics, to be at the factory floor to check that the FAT is done properly. Second, we have talked about this. The software is really important. So you want to check that all the EMS that will be done with the BSS as well as the BMS with PCS, all those tests are done before the FAT and not during the FAT. And finally, it's more for the performance tests that the BSS test should be done at the maximum specification. So for example, if your system is supposed to discharge at a 2C or maybe 3C C rate, it's important that you test at that C rate discharge rate and not at 0.5C, because that will not push your BSS to the maximum. So that's it for my presentation. Here you have also a nice quote from Benjamin Franklin about poor quality. I think that everyone at Sinovoltaics will agree with that. And yeah, so of course, do not hesitate to contact us. We have multiple new offices now. So yeah, do not hesitate to get to know us and get in touch, see how we could help you. But
let me go to yeah, there's two questions coming in. I think it's relevant to quickly answer those as well, because it's FAT related. First one is when the FAT is conducted before shipping out.
Yes, it is correct. The last step at the supplier factory. So to be frank, it's usually in Asia, and so we will visit the factory in Asia, be there for the FAT, and after we give the green light to you, so to the client, in our case to the project developers, to ship from Asia to Europe or to the US.
Right. Okay, and then there's a follow-up question here, again from Eric. What can be done in the factory for testing if the battery energy storage system is first time assembled on site, while from the factory only not yet standalone operational components are shipped? And usually you need full grid support to fully test the BESS, which can be done before shipping at the factory.
So that's a good question. So here there is no one size fits all answer. It's a case by case basis. Some big factories, they have at the factory some testing in place where they can connect PV module, load, grid connections. And so if your components are coming from different areas, it's important to test for the BESS, so the battery side at the factory, ideally with the same PCS that will be used on site. But we can discuss that by email. It's really fine tuning.
Okay. Okay, then one more quick question. Christian asked this question. First is, are the modules disassembled after FAT before shipping, or is the B all batteries mounted?
So here it just depends. First of all, if the batteries can be shipped as part of the BSS, you have some regulations here. Again, it's a case-by-case basis. Some suppliers, they prefer to unmount the battery module. Some others, they prefer to keep it inside. I've seen the two cases, so it's a point to clarify early with your supplier. Oh, I think we lost Dritris, or is it just me? But maybe that you cannot.
Yeah, I just dropped out.
Yeah. Okay. So
Sorry.
I think we can.
My connection just dropped out.
We can move to Claudius.
Thank you very much, Arthur. That was very interesting. And I think it's a really nice fit. I mean, there are a lot of good questions coming in. I hope that some of them will be answered in the course of this webinar. But as Dricus and Arthur already said, we are also happy to get in touch with you afterwards, but also trying to answer as many questions as possible. While Arthur was speaking about everything that happens until the point where components leave the factory, I'm going to speak about the time when everything starts to work from the go live, because risk management of batteries, specifically batteries, does not stop at the end of the factory. You cannot detect all the problems in the factory because battery are degrading components, and their degradation and their performance depends very much on the usage. And for that, I'm going to start sharing my screen. Let me check if that works. Okay, that seems to work. Great. So thank you very much for attending. My name, as introduced, is Claudius Jehle. I'm the CEO and one of the two founders of Analytica Diagnostics. We are a company that is a spin out of the well-known German research institute Fraunhofer. The first monitored batteries that we did is 10 or 11 years ago. In 2012, we were monitoring the first electric buses in Germany, soon to be followed by stationary systems, trucks. We even monitored trains in the past. And we have developed battery diagnostic algorithms for detecting all sorts of problems around battery now for more than 10 years. I'm going to speak about that in just a minute. But the first version of the software that we do that analyzes battery quality in operation, and not, as Arthur said, in the factory, the first versions of this software, which is now called VDX Engine, is more than 8 years in operation. In 2019, we founded Analytica Diagnostics out of the Fraunhofer context, and now we are one of the leading European battery diagnostics companies. And there are not so many out there, so highly specialized companies dealing with quite a complex technology. But let us take the risk of you and take care of this complex analysis. Very brief, what do we do? It's quite simple. We analyze the signals that every battery system generates. Every battery system has sensors for voltage, has sensors for power, has sensors for temperature. And this data is typically collected in a cloud by the manufacturer or by the owner of the plant. But very typically, this data is not analyzed systematically and continuously. Although in this data, there is so much information contained, but you, of course, need some form of software to unlock what is inside. So very important, we do not install additional hardware. We use what is already there. And the software that analyzes this data, we call the VDX engine. VDX is abbreviation for Analytica Diagnostics. And from raw voltage temperature readings, we generate information about profit optimization. How can the utilization be optimized? How can the lifetime of a battery be extended? When is actually the end of life? When do I have to really replace it? After 8 years at the end of the warranty? Or can I use it a bit longer? Also, residual value certification is a very important thing, because sometimes whole farms of batteries get resold. And of course, the buyer needs to know what the quality is to pay a good price. And needless to say, safety and anomaly detection is a very, very, very hot topic. Yeah.
Claudius, there's a question that came in.
Yes.
Question from Darius. He's asking, at each single cell level, is the detection is done on the cell level or battery level?
We analyze. Yeah, thanks for the question. So typically you don't need to do that on every single cell level. We have a patented solution that just uses information from the hottest and the coldest cell, and the cell with the highest voltage and the lowest voltage, to do the anomaly detection. You have tens or hundreds of thousands cells in a BESS, in a BSS. So on analysis on every single cell level would be very, very difficult. But still there are options to perform safety and analysis detection on a smaller data set. And I will come to that in some minutes.
Thanks, Claudius.
So how does that look? So this is a screenshot of the graphical user interface that we provide, but we can also integrate and are actively integrating into SCADA providers, into supervisory control and data acquisition systems, and in other condition monitoring systems. So you get a full overview over the BESS. You can go into detail into every container. You get information about warnings and alerts that are also sent out via email. You get an information on the stress level of your battery. Is your usage condition more stressful or less stressful than initially planned? Can you push it a little bit to the limits? So really a power user tool where you can go very, very deep. But let me show you in the next minutes a bit more detail about it. What we also do next to this continuous monitoring with graphical user interfaces and dashboards is battery health reports, PDF reports with very detailed analysis of the state of health, residual capacity, round trip efficiency, safety issues, statistics. So this is quite a comprehensive offering around everything around the quality of a battery in operation. And as I said, you can get it from us using our graphical user interface and touch points, or we are heavily integrating at the moment into different SCADA providers where you can just embed us. But enough about that. Yeah, some references, and we're currently negotiating contracts for more than 5 gigawatt hours with several players globally, but I'll come to some of them later on. Because I would first like to start to give an overview over battery technology, because this really helps understanding what actually can go wrong and what are the problems that can happen and what deserves attention.
Just a quick question from Giovanni. He's asking, what's the time resolution of the battery data that you use?
The very short answer is 1 reading per second of voltage and current is ideal. We can deal with a little bit lower resolution, but typically 1 second for BESS is available due to the warranty contracts anyway. 1 second.
Okay, thanks.
If you're interested in further reading, I'm writing articles called, or we, not only me, but also my colleagues, the battery cycle, where we deal with what is SOH, what is balancing and inhomogeneities doing. Written in easy language. There's also podcasts in the making. Just get in touch later on. When we speak about lithium-ion technology, there are in our world 3 main types. There's NMC-like, nickel, manganese, cobalt, and there's LFP, lithium iron phosphate, with kind of a renaissance in the last years. And then there are also exotic animals in the zoo, like LTO, titanate, solid state, and whatnot, sodium, iron. We'll not deal with them. Our focus today will be on the typical NMC, which has been really the technology in the past when it comes to automotive and also stationary. They are characterized by always having some nickel contained. They have quite a high energy density and a mediocre lifetime and safety. But increasingly comes this lithium iron phosphate cells from particularly China. They have a lower energy density as the nickel ones, better lifetime, a bit more robust, and they used to be cheaper, but this is not true anymore. They are becoming more expensive. So if you want to be cool on the next cocktail party, you can say, NMC, this is the one that where the lifetime is decreasing over the past years, because as the energy density is becoming higher and higher and higher, they are trading that for some safety and lifetime. And the LFP has a renaissance, this technology mainly coming from China, which has a lower energy density, but as we will see later, which is also much more difficult in operation for very peculiar reasons. So we don't say that LFP will be the only future, because they have some disadvantages as well. And solid state is just the same as here, but the electrolyte replaced by something else. So let's wait for it in the future. It will not be a revolution in the next 5 years. So these cells that come in different forms are put together with electronics and actors and sensors and IoT into different systems. Small systems like that one, 1 kilowatt hour, or a Tesla, which is roughly 100 kilowatt hours. But if we look at a BESS per container, several thousand kilowatt hours or megawatt hours. And so they come in different forms, but in the end, they are all just connections of these cells. And unfortunately, those cells degrade. Let me give you very brief introduction. What is when I use the word cycle and SOC? What is that? SOC is state of charge. This is also what you find on your mobile phone on the top right corner or at your laptop. This is just how full the battery is at the very moment. And the usage profile is characterized by the temperature profile and the current profile, but also by the way you operate the SOC. In this case, you see a 70% swing, starting at 100, going down to 30, and then charging again. This, what we see here, is 2 times a 70% swing, and 2 times 70 is 1.4 full cycle equivalent. So it's as if I have charged my battery 1.4 times full and empty. Battery storage could look like that, idling at 50%, and then frequent dips up and down, where you have a 30% swing and in a 20 to 50% window. Why is that so important? Because this SOC area in which you operate next to temperature is affecting significantly the degradation.
Claudius, can I ask you a quick question? This is from Matthias.
Yes.
Why, despite decreasing NMC lifetime, this is the standard for automotive? Is that true that safety of NMC is going down for the sake of battery density?
Yes, it is not why despite, it is because. No one in a car needs a total mileage of 1 million kilometers. So with the lifetime of the traditional NMC technology, you know all these stories that Teslas, the first Teslas were running 1 million miles. Who needs that? Nobody needs that. So, and there will be a slide later on, but very simple. The automotive industry is optimizing for higher range, and it is okay to go for shorter lifetimes that approach this typical 200,000 miles total mileage. And this is a completely normal trend, and this is an understandable trend. But this makes the NMC technology less applicable to high duty applications, because this higher energy density trading for safety limits because of the automotive industry makes it less fit for 24/7 operation. There are multiple articles out there, and this is a normal trend.
Interesting. And there's another question from Fajri. He's asking, how do we determine the actual battery life cycle? If our available information is the cycle time based on cell temperatures at 25 degrees Celsius, is the cooling system of typical BESS capable to fulfill such conditions in actuality?
Yeah, by using Volitica, for instance, this is exactly what we do. Yeah, we take the life cycle information and the actual usage conditions and make assumptions, or not assumptions, make assessments of the current status of a battery and also predictions how it would evolve under different conditions. This is exactly the topic in the next slides.
So good questions. Keep sending them. Thanks, everyone.
Great. So the usage conditions, temperature, SOC window, the power during operation and charging, but unfortunately also the SOC when you park or when you don't use it, influence these cells, the insides of these cells, which leads to capacity fade, the energy goes down, resistance increase, the efficiency goes down, and safety risks. And we are going to deep dive into these 3 topics. Let's first look at capacity fade, energy going down. Let's look into a battery cell. Let's take a deep look. What happens? So in a battery cell, you have a plus pole, you have a minus pole. You know that from your remote control of the TV. They are connected to whatever is there, a lamp or so. And inside there is a separator, because otherwise you would have an explosion, and a liquid. This liquid is called electrolyte. And inside, ions travel between the plus and minus pole, back and forth, charging, discharging, back and forth all the time. But because it is a chemical system, these ions sometimes make a party with the electrolyte, and they form a passive deposit, a residue inside the cells. They are lost. They cannot transport energy anymore. They form this solid electrolyte interface, and this loss of ions leads to fade of energy over the years. Very simple. You cannot store it anymore because they made a party with someone else. And if you change the usage conditions, you can have more or less stress, and which leads to more or less loss. And we will look into that now. What is the influencing factors? So multiple internal processes lead to degradation. Ions react with the chemicals, the electrolyte. Like all chemical reactions, the speed and extent of these reactions depends on the circumstances. And they are quite complex, and we'll look at that now. Oh, wow, what is that? That is actually a simplified form of how these factors influence power fade, range fade, and safety. And now we're going to look at one of these paths. We are trying to reduce this complexity for you. So how do these factors, the current and temperature profile, how does that affect the energy density? This is a screenshot from a battery cell. I'm zooming in here a bit, yeah? How is this NMC cell influenced by those factors? And let's look at just the SOC swing. So they took 3 battery cells, identical battery cells, and labeled them ABC, or yellow, green, and red. And these 3 ones were used under different conditions. The yellow one was cycled between 70 and 10%, and the red one was cycled between 90 and 30%. So it was always the same energy taken out, always 60%, but in different windows, 90 to 30, 80 to 20, and 70 to 10. And the result of degradation is amazing. Here is what they call the end of life, 80% capacity after some years. And the red one that was cycled between full and 30% lived 2000 cycles. But the one that was used, what the same energy was taken out, but under different conditions, you lived 2 times as long almost. So it was not living 10 years in this example, but 18 years just by changing the usage profile a little bit. This is massive. The influence of usage conditions on lifetime is massive. Now, why did I say end of life? Does this thing look dead? No, it's happily living on. Don't confuse end of life with end of warranty. The warranty conditions end at 80%, but not the life. Batteries live longer than the warranty conditions. Every yogurt and every pizza lives longer than the best before date. Keep that in mind. There is a lot of value behind this wall. Another thing, if you don't operate your battery, but just let it stand around, let it chill, or as we say, idle. It's not used, it's just standing around. Also, this influence can be heavy. If you let it idle fully charged, 100%, in this case, it will be dead after 800 days. But if you reduce it to 80%, it will live 2 times as long. Yeah, warranty conditions are not ending at 80% anymore, 70 or 60%. I just saw that. It very much depends, but it still is valid. Sometimes it's 80%, 60 or 70%, but a hard limit will never be applicable to every individual case. The number doesn't matter. It is just this threshold, this one threshold is not, will not be the future in our opinion. Now, and if you even idle at 50% here, so if you reduce the idle, it will live 4,000 days.
Claudius, question for Matthias. He's asking, so we need to oversize the batteries to ensure longer lifetime?
Exactly. Batteries are oversized by the manufacturers to accommodate the degradation. So to hit the minimum warranty conditions after the minimum warranted lifetime. And because of this oversizing, which is done typically in a kind of a worst case scenario, there is, by optimization of the usage, a lot of room for extending the lifetime if you use it properly.
And then yeah, this is more important make that Julian makes. He says, he's talking about warranty. He says warranty conditions these days are not ending at 80% anymore. General industry is going to 70 or some to 60. I don't know if that's being talked about later on.
Yeah, so this is basically true. So sometimes it is also lower, but what I wanted to say, I wanted to make the point is batteries will live longer than that, even if you have it at 70 or 60%. The reason batteries die or break down, and I'll come to that, yeah, I'll come to that, I'm speeding up a bit, is not directly related to the capacity fade, but to different mechanisms.
Okay, thanks.
I think we will have, yeah, it's very, very cool. Shoot the questions. I'm answering many of them in the following time, so please bear with me for just a minute. So the topic, Julian, you just raised is, does that look dead? So why is it at whatever 70 or 60? And there is no direct relation between the capacity fade and the safety. It's a different story, and I might directly jump there because we're running out of time a little bit. So this is what you expect from a dead battery, really going south, but this doesn't look like it. So I might directly jump there. I think there is nothing else coming. Briefly that. So what does Volutica do here? We continuously analyze all these KPIs. What is the stress level? How stressful is the operation? What is the actual energy capacity? What is the charge capacity? We look at all the efficiencies. The BMS is often not giving all the KPIs or often not accurately. So we are making an independent assessment of that. And of course, we're also making recommendations how to reduce the stress level and increase the lifetime in our dashboards, in the reports. And I'm skipping the point of availability for the moment to directly jump to the anomalies, because this is something that seems to be very, very much asked here. And in the meantime, I can answer another question.
Yeah, let me pull up another question. This is maybe not directly related, but this is from Abhishek about the type of cooling. What's preferred, air-cooled or liquid-cooled cooling, battery cooling?
This is very much a question of how the manufacturer built the systems. We have to be fair here. They are the experts, definitely the experts in building the systems. And the short answer is, if you have enough money, liquid cooled is typically always better, because it transports away the excess heat more efficiently and leads to a more equal cooling, even on the smallest scales. So what that does is it avoids inhomogeneous degradation. We just learned that next to this SOC window in which you operate and the charge rate or power with which you charge and discharge, the temperature is definitely very much affecting the degradation. Now, if you have in a module with several dozen cells, an inhomogeneous temperature distribution, this leads to inhomogeneous degradation. Some cells on the outside will degrade slower than on the inside, where you cannot get rid of the heat, which will in the long run very, very likely lead to availability and or sometimes even safety problems. But there are sophisticated air cooling systems that are also good. And I'm not judging what the manufacturers would come up with innovative things.
Okay, ton of questions coming in. every explanation, there's 2-3 other questions coming. So just going back, questions from Christian, because otherwise it might not be relevant anymore. He was asking, is this also applicable to LFP cells? Following this, would you recommend NMC LFP for UPS functions? And between brackets, he's saying for later on related to capacity fade in standby. Not sure if that question is still relevant.
LFP is like a zoo. Yeah, we are speaking about animals with 4 legs and animals with 2 legs. Yeah, there are so many elephants and dogs and cats, so it's very difficult to just separate LFP and NMC in this large group of animals. There is simplifying LFP. The animals of LFP with all their sub animals are less prone, less sensitive, less susceptible to parking and idling at higher SOCs than NMC. NMC is, but there are exceptions, NMC is very much more susceptible to change, to extreme usage conditions. So for UPS, LFP is probably a better choice, probably. But unfortunately, we now skip the availability part for time reasons, and LFP systems tend to, if you don't monitor them well, tend to have more availability problems due to their flat OCD curve for the nerds among you than NMC. NMC are typically better to manage. So if you want a high availability and low degradation, it's a difficult thing, because LFP, availability issues maybe.
Right. Okay.
Now, when is the end of life? Not the end of warranty. When is end of life? And end of life is, in our opinion, when a battery is not usable for a purpose anymore. When the energy capacity has dropped too low, the efficiency has dropped too low, or very simple, when it just stops working entirely. And when is that? Well, that depends on the use case and not just on a limit like 60, 70 or whatever, 80% SOH. And what I want to show you here is that the breakdown and maybe even fires, which is rare, is not the same as this capacity fade thing that we were speaking about. And I really love that. I think I stole it from another webinar. I love it. How did you go bankrupt? Like, how did you go end of life? 2 ways, gradually. This was what we were speaking about. Then suddenly. Great. Now let's look at that path. How does the usage influence fire or normal end of life and breakdown? Skipping that. First, the disclaimer, yeah. I am not the one that says batteries often burn. They burn very, very rarely compared to the overall installed capacity. But if they burn, it is definitely a problem. Now, it is estimated by experts that the biggest part of all fires is not due to the battery cells themselves, but overheating cables, loose plugs, chargers, peripheries. Very difficult to detect. Quality problems. That's why do factory acceptance tests. And a lower part, like 1/3 or 1/4 of them, is probably because of the batteries themselves, because they can become difficult. We wrote an article about that with some experts. If you want this article, just text me. Now, you remember that this partying with the electrolyte leads to capacity fade, which leads to these curves that we were seeing before. And definitely this is very much due to the external influencing factors, temperature, current, and SOC. But there are certain usage conditions which lead to a party of the ions with themselves. They don't form a passive residue, they form metallic lithium in the cells. Lithium plating is it called. And this also, of course, leads to capacity fade, because again, the lithium ions are not available for charge transfer anymore. But as this grows, it can lead to internal defects. And this is really problematic because these internal defects are very difficult for the electronics to be detected. Yeah, not all of them are dangerous, but for instance, lithium plating it's usage induced and it's difficult to completely avoid, and long-term trends indicate it, and they are difficult to detect without monitoring and electronics that do it. And this one, what I was mentioning before, sorry, this is a quite complex sketch. Let me unfold it for you. Years ago, we were starting with NMC, ignore the number 333. This was some years ago, 5 to 10 years ago. Today, the trend pushed the energy density 30–40% up to NMC 811. Here's the energy density written on this plot. So the energy density raised and raised and raised. But the thermal stability went down a bit because there is no such thing as a free lunch. So the susceptibility of the NMC technology is increasing and increasing and increasing. So this will lead automatically to a higher relevance of other factors around the battery storages for monitoring. I'm not saying they're becoming unsafe. We are just trading one thing for another, and we need to raise the way we look at the battery systems. In Korea, there is rumors or numbers, estimations that 2% of BESS systems burned because of electronics problems and wiring problems, and also because of battery problems. And as I said before, LFP is really less hard to ignite, is harder to ignite, less susceptible, but still if they burn, they are burning also very violently. So don't just buy LFP and think they are safe inheritedly. They can also cause some form of safety risks. And this is also recognized by the insurance industry. The CRO forum, the Chief Risk Officer Forum, headed by Allianz and Swiss Re, this year issued this white paper at the beginning of the year, stressing the importance of performance monitoring of battery cells in the future as one of their emerging risks. I'm skipping that. He is a professor, Professor Paul Christensen from Newcastle. He really stresses the need of data analytics, which I really like, of course, because several of these trends are difficult to detect without data analytics. So what do we do? And then I'm done for the moment and happy to answer more questions. Is continuous anomaly detection for critical anomaly KPIs, thermal anomalies we continuously analyze, balancing and symmetry anomalies that can lead to availability issues, and cell quality and safety anomalies. This is one algorithm, but these two outputs, just based on very thin data, we continuously alert on them. We have a trend alerting algorithm on top that sends out emails and notifications and makes recommendations for the mitigation of these problems. And of course, we also do awareness training for the personnel out there. And this is all contained in our software solution. this is how it looks. Yeah. So you get notifications about all the different problems. And if you click the link, you can investigate what's going wrong and optimize your operation and maintenance teams. And I want, just probably not going deep into that now, finishing with a real life example, skipping that for the moment. I want to highlight and thank Sinovoltaics for the opportunity of this joint webinar. And the risk management doesn't stop with the go live. We really want to offer joint offerings in the future, starting from the factory, but then ongoing into the life of the batteries. Now, some more questions, please.
All right, let's look at a few more questions. I'm just going to pull up a few. So here's a question from Haroon. He says, what should be the optimum ambient temperature for keeping batteries as we're experiencing very high temperature in our region, in Pakistan?
Normally, these batteries should come cooled, as we said before, so air-cooled or liquid-cooled. And this is something that you should put into the tender because the cooling system takes care of the climatization.
All right. Next question. When using liquid cooling, is there any risk or recorded events of coolant leaking into the battery bank / modules and short-circuited the batteries?
We have heard about it, but this is a technological risk that we see continuously being handled quite well by the manufacturers, because obviously they know that very well. This is very critical. One thing, because many questions are around cooling, for BESS systems, we don't see so much problems with the cooling and temperature. They are well controlled. The larger problems come from different areas. We also hear that very often, cooling temperature. As I showed to you, the SOC window in which you operate and the usage conditions more globally. This is where you should put your attention, not only the
so there's exactly a question about that while we're talking about that topic. It's from Andre. He's saying, looking at the graph of chilling, the lower SOC, the better. Why so manufacturers leave cell / module with SOC of around 30%, not lower? Too much risk of deep under voltage, or there are some other reasons?
Again, this is not entirely true, because in the zoo of all the animals, there are. I just picked one example when going to this graph of temperature. Oh, actually, I didn't even show it. So it is not entirely true that the lower the SOC, the better. In this example, it is the better. Yeah, you're right. The lower, the better. The 30% is a compromise between charging too low, as you said, and also transporting it. There are transport regulations in place that limit it to 30%. So in a way, you're right. It's a mixture between not discharging too deep, which can also be less beneficial, but also external factors, how you are allowed to transport that.
Right. Okay, another question. It's about the depth of discharge. Is the DoD problematic solved with just using the SOC between 10 and 90%?
The short answer is depends on the cells you use, because I'm again just picking examples here. Sometimes battery cells are very susceptible to that range. The ballpark figure is for LFP and NMC. The higher the swing, the DoD, I don't like the word, the swing. The higher the swing or the window, the more problematic. But it is good if you don't go to the extremes as a ballpark figure. So instead of going, in your example, from 100 to 20, it is probably better to go from 90 to 10, correct?
Okay. Then there's someone here that likes to test a storage system combined with an EV charging system, DC-DC. Is this possible? Can we test this? Of course, that's what we do. So we'll reach out. Glad to help with that. Other question, Abhishek. He's maybe a question for Arthur. Arthur, what are the major tests conducted on battery at FAT other than charge and discharge test?
Yeah, sure. So as we have seen, there are some visual checks. Also, we'll also confirm that each component is working well on its own. And after, maybe your question is more on the performance test. So of course, we'll do charge discharge. We'll also check how fast does the BSS react to the commands. And also we do some safety tests. So we will simulate a shutdown of the BSS and how the BSS reacts to that.
Okay, and if I may add something to this, we have an ebook on the website about battery energy storage, and all the factory acceptance tests are listed in there. The ones that we highly recommend to perform. Let me share the link here. It's been released a few months ago, but if you haven't seen it yet, it's certainly 2023 relevant. So feel free to have a look. Let me see. There's still more questions. Question here: how safe is LMO? Some manufacturers give hybrid LMO plus NMC.
Yep, I made a simplification, like I made a lot of simplifications actually. And I just was lazy and grouped LMO under the NMC-like ones. So again, it depends on which year and which version and revision, but by and large, they are more related to NMC than to LFP and share more similarities to what I explained for NMC than for LFP. This is one of the largest issues, by the way, that we have these two categories or three categories in mind. But again, under those come a lot of different technologies. Some are optimized for that, some are optimized for that. Difficult to generalize.
Okay.
Just get in touch with us. We can help you.
So this is a related question. Does your analytics platform consider different cell characteristics from different manufacturers?
Absolutely, because we need to be able to analyze BESS and batteries from all different manufacturers. So yes, of course.
Okay. Then here another question: what percentage of cycle life will be reduced when operation T is improved from 25 to 45 degrees?
The rule of thumb is if you go up 10 degrees centigrade, you double the rate of degradation. So you will destroy, in that case, your battery in just in less than half the time. Never do that, please.
Yeah, that's a good argument for proper cooling. Okay.
Especially for storage, this is horrible.
So this,
like idle.
This question from Romil is also related. To increase the battery life, what would be the best C rating for charging and discharging?
You might hate me. I'm like a lawyer, and again, I have to say it depends. It depends on which cell type you're implementing. Very much, if you use a cell type that is optimized for fast charging, then you can use 2C, 3C. But again, to not just answer like that, the lower the C rate, the better. Anything like normal technology, yeah, is anything below or equal to 1C in charging and discharging is absolutely unproblematic. Just by charging is important. Charging at 1C and the temperature is lower than 20 degrees or 15 degrees, this is not good, because this is one of the situations where that can facilitate lithium plating. So under 1C, you're happy, and over 1C, it depends on the exact chemistry that you're using.
Okay, I think we're getting through the questions. I have one more. Actually, two more, but one you already answered. I believe that this one. What are some examples of LFP fire root cause? Because you explained earlier that only a quarter of fires are caused by the actual battery cells, and 75% are caused by other components like heating cables and malfunction in chargers, etc. I thought that was a very interesting insight. Is there any more to elaborate on?
Yeah, I avoided to put numbers here because it's just an estimation, because there is unfortunately not so much transparency out there. But yeah, the most LFP fires that we have seen, let's say, I mean, they are still very rare, are not caused by plating. But there are counterexamples. This guy, the one that I showed to you, Paul Christensen has an extensive book of fires, and there are LFP fires that are thought to be caused by the LFP cells themselves. The big problem is when these things burn, everything is lost. So it's difficult to do a root cause analysis if you don't have monitoring before, and this was not the case in many cases. Difficult to answer, unfortunately.
Okay. We have to be mindful about time. So one more question here. Previous question was from Julie, by the way. Thanks, Julie. This one is from Cam. Final question. Does the software monitor warranty violations?
Yes, and also near warranty violations, because if you're just informed that you violated the warranty, it's too late. So warranty violations and near hits, yeah, if you come close to violating them.
That's very good news for the owner of the system, I would say. Maybe less for the factories, because you will have a really close step on your systems. With PV modules, that's still, of course, you can investigate for warranty violations, but to have that real time is next level. So that's very, very useful. Okay, well, everyone, that was the final question. I've learned a lot, and I'm sure, I hope many of you as well. I think when you're hearing this, when you're building battery energy storage systems, proper solid diagnostics are a must. And Politica is a key player in this industry. And please feel free to reach out. Maybe if I can pull up the presentation just to have your contact details, Claudius, at the end, that would be useful if people want to reach out. Feel free to get in touch, either with Politica for diagnostics, and if you want to safely procure your battery energy storage from the factories in Asia, you know where to find us. Thank you very much. Questions were tremendous. Thanks for joining, and yeah, getting towards the end of the presentation for the contact details. Let's see. We can skip.
Yeah, you can just also go to the website and send it to contact@Politica. It will reach us. And thank you, Christine, Mateusz. Yeah, there will be new articles on sustainable bus soon.
All right.
Thank you, everybody. Thank you, thank you, Sinovoltaics, everybody. Thank you for the questions. Dricus, thank you very much. Arthur, Sylvia, for organizing it. Amazing.
Thank you too. All right.
See you soon.
Thanks, everyone. See you on the next webinar. Bye-bye.
Bye, everyone. Bye.
Visit sinovoltaics.com to learn more.